Okay, I soldered up the board. I haven't powered it up yet because I want to do this live on camera. But before I do that, I'd like to discuss a few problems I had with my design. I already told you that I'm lacking this diode around the regulator, but it turns out that there is also another problem with the regulator. And I'm going to demonstrate that on a spare board because it's just easier to see. This is a 10 volts regulator that is powered from around 13.5 volts. So there is a drop of 3.5 volts across it. And if I'm assuming that I'm pulling round about 1 amp, that's 3.5 watts that this regulator has to dissipate. Now at 3.5 watts, I haven't checked the exact figures, but if you operate this guy without heatsink, I'd assume around maybe a temperature increase of 20 degrees above ambient per watt. And for 3.5 watts, that's 20, 40, 60, 70 degrees centigrade, that is, above ambient. So that's going to be around about 100 degrees, and that's really not that great because that's very close to the thermal shutdown temperature, and it's too high anyway. So this guy absolutely has to be mounted on a heatsink. And my original idea was to insert it like that. This is the side where I have all the connectors, as you can see here, and I just wanted to have this guy stick out like that, and then mount it on the case or something. But unfortunately, I messed up the footprint. In fact, I had a bit of trouble when I designed this because for some reason the symbol in KiCad didn't match up with the footprint, and I had to change the footprint, and I triple checked it, and I noticed that on the Silkscreen there is actually this sort of ball side here is where the tap is that you can mount on the heatsink. And I looked at it and was like, yeah, okay, I have the wrong like Silkscreen designator here, but I don't really care. But it turns out that in the end it was correct, and I messed it up. So I have two options. I cannot mount it like that because that would be reversed. So either I mount it like that, or I mount it on the other side like that. And that has the advantage of the tap being to the side, such that I can mount it on a heatsink, because if I do it on the other side like that, I don't have space for a heatsink because I've got all these connectors in the way here. So I decided to put it on that side instead, and unfortunately now my board cannot lie flush on the table. But so that was a little issue I had. But luckily I was able to catch that before I actually soldered the part in. The second issue is with the Silkscreen on the DC to DC converter part. I really hope that you can see that on camera, but if you look at this connector here, I don't have polarized connectors. That was a decision I made on purpose, but I always put like little ground symbols on the board, hopefully to never get this reversed. But anyway, the ground symbol is here, which means that this guy should be ground, but if you look closely, the thermal relief to the ground plane is actually on the connector at the bottom. So unfortunately this ground symbol is completely wrong, and that's sort of very bad because you put these ground symbols on purpose for never doing this wrong, and it really doesn't help if the symbol itself is on the wrong pin of the connector. But anyway, that's it. So I haven't powered it up yet. I will do this next. I will do it on camera because many people, sometimes they do things when the camera is not running, and then they go like, oh no, it blew up. So in case this is going to blow, I want to catch that on camera just for the kicks of it. Although I buzzed it out, and I don't think there is anything seriously wrong with it. But anyway, let me change the setup and then we'll power it up. I'm ready to power up the board now. I have two wires connected here to the voltage input, and I will apply 12 volts to that. I really should be applying 13.5 or something, but unfortunately my main supply is used in a semi-fixed experiment rig right now, and I cannot turn that off. So, and my other supply doesn't go up to 13 volts. So I'm going to use 12 volts here. That's not ideal because this 10 volts regulator needs some headroom, especially if you're drawing a lot of current. But we'll get to that. In addition to that, unfortunately, the supply I'm using now is a switch mode supply. So when we're going to do some transient measurements, ripple measurements, we're going to see that switching supply. But that's not the supply I'm intending to use when everything is built up. That's just for some rough testing right now. So I will measure, first I will measure the 12 volts that I'm applying. Then I'm going to measure the 10 volts that come out of the regulator, and I'm going to measure 5 volts from the local regulator that is powering the logic. As soon as I plug this thing in, there should be an LED coming on the board. So if you see blue smoke, it's bad. If you see a blue LED shining, it's good. So give me a second to turn that on, and this seems to work. I'm drawing around 1 milliamp, so that's probably just the LED and not much more. And this crocodile clamp here is connected to the commons of my multimeter, and it's actually hooked up to the tap of the regulator, because the tap and the center pin are connected. So that's just an easy way for me to get access to ground. So let's do some measurements then. First, I'm going to measure the 12 volts that are coming straight from the supply, and I'm going to use this header over here. This is just a this is a header that you can use for the feed through to the 20 volts charge pump. So if I measure that, I'm measuring 11.94 volts. So that's fine. Then trying to measure the 10 volts here, I get 10 volts bang on, so that's fine as well. And lastly, if I try to measure the 5 volts rail, that's 4.95, and I'm actually going to measure all of my logic chips, but it's always 4.95, so that's fine. So the next thing I want to do is I want to load down the 10 volts rail, because as I said, I'm not using 13.5 volts at the input, because at 13.5 volts the regulator should be able to provide around about 1.5 amps. But with lower an input voltage, I'm expecting to see a drop if I draw maybe half an amp or something at the output, because there is just not enough headroom for the regulator to regulate, so the output is going to drop. And I'm going to figure out how much current I can draw and write that down, because I like to keep notes on my things. In fact, if you know me, you know that I'm a very messy person, so if I keep notes on things and I try to keep things organized, this is really a sign that it's absolutely necessary to have some order in some things. So and I put all the sheets I'm showing and also my calculations in a binder and stuff. So this is very important, because otherwise you really lose your measurements and not know exactly about your particular device. So I want to make some rough measurements right now, write them all down to know what I can expect as I continue with building. So unfortunately, it just occurred to me that I couldn't do this loading test reliably right now, and the reason for that is that I don't have the proper cabling to do this. So instead of not showing that, I thought, first of all, this is a project log, so I'm supposed to load the fails as well. And second, I'm trying to make some educational stuff here, so that might be interesting nonetheless. What I have here is my Homebrew dummy load. You can get some of these commercially. They tend to be fairly expensive, and I never felt the need for anything better than this little guy here. That is essentially just a bunch of operational amplifier and a FET that dissipates. some current that you can set here. So you use these devices to draw a fixed amount of current, let's say 1 amp or 2 amps. And if you're designing a power supply, you then poke around your power supply and check whether things behave the way they should at a fixed load. Of course, you can also use a power resistor, but the advantage here is that you can set the current to an arbitrary value. This meter here displays the voltage across these input terminals, and this meter here displays the current that the device is drawing. Of course, this depends on the position of this knob. In addition, I have the fluke connected up to the 10 volts rail of my control board, and that's also the rail I'm using for my test. So this meter here should in theory measure exactly the same that my fluke is measuring. However, if there is resistance in these leads here, there is going to be a drop across these wires, and this meter here is going to read less than this one. Although apart from the cables getting warm, that's not that big an issue. Because all you want to do is you want to draw some current, and you don't really care whether you've got some drop in these wires, because this device is going to correct for that and is going to draw that current nonetheless. So that's not the problem. The problem is the input. Besides that, these wires here are rated for something like 3 amps, so I wouldn't expect that large a drop across them. Anyway, so let me power this up and then we'll see what happens. Okay. So this is powered up. I'm not drawing any substantial current. I've got 10 volts across these rails, and also my fluke is sending me 10 volts across the rails. But as soon as I start to draw some current, and I'm trying to do that in a way my hand doesn't get in the way. So let's say I'm drawing 500 milliamps, and my 10 volt rail has dropped to 9.65 volts, so that's bad, obviously. And also it's hard to see on the analog meter, but the same happened here. So why is that? I'm drawing 500 milliamps and I lost regulation. The reason for that is actually my 12 volt input is not 12 volts anymore. I'm disconnecting now the fluke from the 10 volts rail, and I'm measuring the 12 volts input, and it's only 11.2 volts, so the regulator only has a headroom of 1.2 volts to regulate, and that's just not sufficient. And the reason that I only have 11.2 volts here and not 12 is that there is a drop in the wiring from the supply to the board, and of yeah, let's measure that again, of 0.8, yeah, of 0.8 volts, so that's 0.4 volts per lead, and I really should get better cabling, especially because I'm using to power this stuff, I'm using like these little wires that you saw before, and okay, they're not getting warm, but still that's certainly not the best wire for sort of a connection that's supposed to deliver a fair amount of current. So unfortunately, all the stuff I want to do now and in the next few videos do not require a lot of current, so that gives me some time to get proper wiring. Of course, I could also solder something up real quick, but I want to get proper wiring for this, so I'll get that and continue with the other stuff in parallel. The last thing I have to check is the voltage doubler that I have on this board. Now, ideally I would like to measure the ripple I have on that 24 volts output. But in the meantime, I figured that the power supply that I'm using has a ripple of around about 75 millivolts on its output. So any kind of ripple that I would measure or at least should be far lower than 75 millivolts, so that's just not going to cut it, and I'm going to leave out that measurement for now. But I can measure the output, and the output should be about double the input. Let's see. Okay, that's 23.5 volts. So let's think for a second. I'm feeding in 11.95 volts. Multiply this by 2 will give me 23.9 volts, and I have 23.5, so I have 400 millivolts lost due to suboptimal efficiency. And I think this is fine. I'm going to double check with the documentation of this project, but so far I'm quite happy with that. To test the I/O, I fired up the Spectrum Analyzer software, and you can see that this is already running, this is already sweeping and measuring, but because I haven't hooked up anything to the control board, it's not measuring anything, obviously. So let's halt that and go to Setup and Special Tests, which brings up a screen that you can't see here on camera, but in that screen I essentially click out PT port test, which brings up this little guy here. And I'm going to do the following. I have my fluke here. Let me check that. You can see that on camera. Yep. And it's measuring 0 volts. This is now connected to bit number 7 of connector number 4. And apparently that guy is low. So if I twiddle around with this bit number 7 here, there is no change because the latch line is low. So this should actually change the logic level on the LPT port, but that should not be reflected on any of my output ports. So I have to figure out which latch I have to enable. If I check my schematic, there is latch number 4 is connected to the strobe, to the data strobe line. So that's the latch enable, and if I pull that guy high, I hopefully will be able to measure a logic high. So let's try that. Yes! You know, it's funny because I've been doing this for 20 years now and I can still get excited about the pin changing its logic state. But anyway, so now that the latch is high, if I pull this guy low, it goes back to low because since the latch is high, the input is directly reflected at the output. So this works, and if I pull the latch enable line low again and then turn the pin to low, this should remain at 4.95 volts, which it does. So this seems to work. Now, I could check all the combinations, but I have something else in mind, so I'll come back to that. But before, I want to check something else. Remember that I have not populated the pull-ups for the input, in the hope that there are already pull-ups in the computer. So I'm going to measure that. If I disconnect my multimeter probe and measure the header, I should be able to figure that out, because remember that these pull-ups are not populated and there is nothing connected to this header. So if there is a pull-up inside the computer, I will measure, let's say, between 4 and 5 volts on this header because it's pulled up by the pull-up inside the computer. However, if I'm not going to measure anything between 4 and 5 volts, I don't have pull-ups inside my computer, so I will have to go back and populate these. So let's measure that. And yes, 4.5 volts. So this is fine, and it means that I don't have to put the pull-ups because they're already in my computer, which is nice as well. And in fact, if I click this capture status button here, it's telling me that all of these status lines are high. Now if I take a jumper wire, if I manage to find one, here's one, connect one end to ground and the other end, for example, to the phase input, I essentially pull the line low now. And if I click capture status again, I see that one of the status lines is low. So this seems to work, and I'm just going to do that for all of the 4 status lines. That is weight going low, so that's fine as well. That one works as well. And the 4th one works as well. And I haven't connected the air pin. So that works as well. And in fact, if I close this and get my meter out of the way and start this little guy again, and then pull low the magnitude voltage line, this should actually be reflected on the screen, which it is. Now, I'm measuring 0 dB because it's constantly sending low. So that works. To conclude the I/O testing, I want to test the outputs a little bit more thoroughly because I know from experience that it's very annoying if you have a problem there, you're trying to debug something and you don't really realize that your I/O is not working. So what I'm going to do is I'll take this thing here, which is a small logic analyzer. Actually, you can get this from Dangerous Prototypes for about $50 or so, and this allows me to measure quite a number of logic channels simultaneously. In particular, this guy has 16 input channels, and you can extend this by attaching some more inputs here, although you need a buffer, but anyway, I can use these pins up here directly. I'm using this as a FPGA development board usually, but this is meant to be a logic analyzer, and I'm going to connect one input of my 4 latches to bit number 0 to 7 and iterate from 0 to 255 and measure what I get. So I need a couple of minutes to set everything up, and then I'm going to show you the code and my experiment. Okay, so what I've done is I've connected the logic analyzer to port 1 on the board. That's the first of the 4 output ports I have. I connected all the 8 lines, and I wrote a bit of Python code. Now I really hope that you can read that on screen. In case you can't, I'm going to walk you through anyway, but I'll also put the code online as usual. Now what I'm doing here is first I import the parallel module, and that allows me to interact with the parallel port in Python. Then I'm initializing that module, and then I have a bunch of functions. The first function is the reset function here. The reset function first sets all the data to 0 on the parallel port. So every of the 8 data lines that I have will be on the logic low level because that's just what 0 is. The argument here, you can pass an integer and it's going to interpret that as binary value and set each of the bits of the data port accordingly. And then I'm toggling each of the 4 ports. Now, what these toggle functions do is they first set the latch enable of the corresponding port 1 to 4 on the output to low, in case it's not, then pull it high and set it low again. So this will just latch in whatever value I have on my data byte, and I can do this for each of the 4 ports. That's why I have 4 of them. And then, let me scroll down a little bit. That's toggle 4. And this is the code that I'm essentially executing then. First I call reset, which sets everything to 0. And then I iterate an integer from 0 to 255. Or actually, that should be 256 because Python does not take the last one. So that goes from 0 to 255. And then I set the data port to whatever my current integer is, and I toggle each of the 4 ports. So that should first start with 0, and then set port number 1 to 0, port number 2 to 0, port number 3 to 0, and port number 4 to 0. And then in the next iteration, I is 1. So that will first set the data register to 1, but nothing will happen on the output because the latches are all low. But then this will toggle the first port, so the first port will go to 1, and then the second port will go to 1, the third port will go to 1, and the fourth port will go to 1. And in the end, I just reset the whole thing again. Now, the second part of this setup is the logic analyzer software, which I have here. And this just allows me to display whatever I have on my 8 channels here. In addition, in this summary line here, I get a hex value of the value that is represented by each of these 8 bits here. And lastly, I also have a scope line here that just as far as I understand, displays that byte value in a graphical way. And the way this works is I can go to capture and begin capture. And the most important part here is to get the proper sampling rate. Now, I have experimented with this a little bit, so I know what I can expect. But in the end, the key here is that if your sampling rate is too low, then you're going to miss on things that happen on the bus because you're just not sampling when something of interest is happening. If you set the sampling rate too high, in the end, you're just going to be able to measure for a less amount of time. So I have this set to 100 kilohertz because I did a bunch of tests before, and I can also trigger, but currently my trigger is disabled. So as soon as I click on capture here, it's going to take a measurement, and it displays all low in the end. So if I rerun this and now enable the trigger, I can trigger on bit 0, and this will just arm the trigger and then wait until bit number 0 becomes logic high, and then start with the acquisition of the measurements. So if I click on capture, now this sits essentially as long as I want, because when I don't do anything with my board, the trigger is just armed and waiting for bit number 0 to get high. So if I go back to my Python code and run the thing, I can see that it already took an acquisition. And because I'm just counting from 0 to 255, I can see that bit number 0 is toggling pretty fast, and bit number 7 is just toggling once. That's at 128. And in addition, the graphical representation of this shows me that this is steadily increasing, there is no glitches whatsoever, so this looks pretty nice. I can also zoom in and see that this is really increasing every time by 1. So that's 59, 5A, 5B, 5C, 5D, and so on. So what I will do is I will do this for each of the 4 ports, and in case you don't hear any reports on a failure, you can assume that this worked just fine. What I also have to do here is, because I'm setting port 1 to some integer, then port 2, port 3, and port 4, I have to make sure that this is evenly spaced here. If it's not, it means that when I want to set, let's say, port 1, I might set port 2 simultaneously. Of course, that would be a mistake. Maybe the 2 latch lines are shorted or something like that. So I have to make sure that this is not happening. In addition, there is something very important to note here. This is a normal process, a Python process on this operating system. So the kernel might decide that this process should be interrupted. So I actually ran this a few times. Maybe I can retry and see whether I can capture that. But it doesn't happen so frequently. Yeah, you don't see that very well, but in the end, it might be the case that the process gets interrupted and this is not evenly spaced here, so that's something to watch out. And lastly, I was actually interested in that, how fast can you go? Because if I measure here the duration it takes for one of these guys to remain low, that is, if I go to my measurements and measure the time difference between these two cursors that I added, this is roughly 600 microseconds. So that's far slower than the parallel interface would in theory be able to get out. But as you can see, there is no weight or anything in my Python code. So that's probably, if you do it that way, as fast as it gets. The last thing I want to know is how fast is the spectrum analyzer software sampling? And I want to know that just out of pure interest and maybe to get a better grasp of the hard-end software, but this is not critical for the hardware I'm building here. Anyway, so to do that, I have the logic analyzer hooked up to port number 3 of the control board. And this port number 3 has two lines that go to the ADC. Well, of course, I don't have an ADC yet, but in the end they will. One line will tell the ADC to take a measurement. That will just be a short pulse. And the other line is a clock line to shift out the measurement and back to the control board and eventually to the PC. So this will just tell the ADC to send back the next bit of the measurement. So let's have a look at that. I'm going first to start the spectrum analyzer software again. So this is running, and then I will take a measurement with the logic analyzer software, and this looks nice, and stop the spectrum analyzer software again. Have a closer look at this data. Now the data on channel number 6 is the clock I was talking about, and the data on channel number 7 is that burst to tell the ADC to take a measurement. And in fact, if I look at this, this has a period of 850 microseconds, and interestingly this comes sort of in two bursts, and then there is a longer waiting period of 4 milliseconds, 4.25 milliseconds, and then two bursts again. So that is kind of slower than what I would have expected. In fact, if I look at the two bursts, this runs at a frequency of 1.17 kilohertz. While technically the ADC is able to take 250 kilosamples per second. So I'm not really sure what's going on there, but maybe this is slower for a particular reason. Anyway, I'm not too concerned about that. This is just something I wanted to know. And if I zoom into this yet again, I can see that there is this pulse here that tells the ADC to sample, and then the clock should shift out 16 bits. So there's two things to note here. First, this is not evenly spaced. This could be because I'm sampling at too low a sampling rate with the logic analyzer, or it could also be that, and this is just due to the fact that this is an operating system that, as I explained before, is able to interrupt the process and do something else. But anyway, I'm going to try and count the rising edges because I'm wondering how many these are. I'm expecting to have 16, and I'll stop the camera because I have to focus a little bit to count these. So interestingly, I'm counting just 15 rising edges. And I'm not really sure why this is, but probably the one of the bits is already present without the need of a clock pulse. So anyway, I'm sure this is correct as well. I was just wondering about the internals of this. So that essentially concludes the testing of the control board. To summarize, all the voltages were correct. I wasn't able to take the ripple measurement of the DC to DC converter because of crappy power supply that I have. But other than that, the voltages seem to be fine. The I/O seems to work nicely as well. I was a bit concerned about, I haven't shown you this, but I'm using this sort of ribbon cable here to connect the parallel port to the control board. And from a transmission line perspective, this is not the greatest. So I was concerned about that, but this seems to work nicely. So the next step is to build up the ADC and to test the ADC. I hope that was interesting. In case you have anything to add, please do so in the comments, and thank you for watching.